Hey everyone, in this video, I'm going to be talking about free energy. In this video, we're going to identify the types of reactions that are involved with free energy. We're going to describe the changes in free energy for both reactions. We're going to explain the role of ATP, and we're going to identify types of the various reactions. In both of these concepts, we are going to be looking at how energy changes occur over the progress of reaction. And we can compare these two types of reactions depending on whether or not the change in energy is positive or negative. So along my x-axis, I have the progress of the reaction, and along the y-axis, I have the amount of energy in the system. So the first type of reaction we're going to talk about is what's known as an exergonic reaction. In exergonic reactions, the amount of energy that's available in the substrate is more than the amount of energy that's left in the products. So your graph would start off something like this. Let's say that our substrates have 20 units of energy at the beginning of the reaction. Now those 20 units of energy are stored in the chemical bonds, that is the shared electrons between these molecules. And the product in an exergonic reaction has less energy than the substrate. So I'm just going to say 4 as a random number as the amount of energy that's in the products. And so you can see that when we calculate the change in energy, which is the final minus the initial, we get that change in energy to be negative. So in this case, it's negative 16, but that's just our example. So what we would write is that the delta G, or change in free energy of the reaction, is negative. These types of reactions are typically where you have a substrate being broken into a product. So we call these catabolic reactions, or that they're involving catabolic enzymes. And so we've already talked an example of this from Unit 1 when we talked about hydrolysis. But we're also going to see cellular respiration as an example of an exergonic reaction. Now, all reactions have an initial amount of energy that must first be invested to get the reaction started. And this is what's known as an activation energy. And so when we look at the shape of this graph, and include the activation energy, our graph is going to look something like this. And this section in here is going to represent what's known as the transition state. In order to get to the transition state, which is unstable, you need to input the activation energy first. So your activation energy would be this amount. So E sub A is the energy of activation. Now, when we add an enzyme to this reaction, we're going to change the amount of energy required to get it started. In other words, the energy of activation. Enzymes are not going to change the amount of energy that's in the substrate, nor they're going to change your product. So overall, your delta G is still going to be the same when you compare the amount of substrate to product. But the enzyme is going to change the energy of activation by lowering it. And that'll allow the reaction to occur much faster, which is why enzymes are known as organic catalysts. Now, in this example, there were 16 units of energy between the product and the substrate. And those 16 units of energy are not all useful energy. Some of this energy, so 14 minus 20 is negative 16, some of that energy is going to be lost as heat to the environment. But there will be a very small portion of the energy that is lost in this reaction that's going to be used to power endergonic reactions. In other words, they are going to be transferred from this breaking reaction into a building reaction. So let's talk about those endergonic reactions. Endergonic reactions are the opposite of exergonic reactions. And so to make things simple, I'm going to keep the y-axis on this side over here, but still have the same direction for my progress. So the energy that's not being lost as heat is going to transfer to these endergonic reactions, which are the opposite of exergonic reactions. So if exergonic reactions have a negative delta G, then endergonic reactions are going to have a positive delta G. Since exergonic reactions are using catabolic enzymes, endergonic reactions are going to use anabolic enzymes. And so the opposite of hydrolysis is going to be dehydration synthesis. And we're going to look at how photosynthesis is another example. In exergonic reactions, the substrates contain more energy than the product. That means that in endergonic reactions, the substrates are going to contain less energy than the product. So we're going to put our substrates down here, and the product is going to be up here. Now, there's still going to be that energy of activation that's going to be present, but in addition to the energy of activation, you're going to have to provide additional energy to create new bonds. In both cases, whether it's exergonic or endergonic, they both are going to require input of energy, and they are also going to release energy in the process. The difference is that ratio of how much energy is input versus how much energy comes out of the reaction. Now, the energy transfer between exergonic reactions and endergonic reactions is not direct. So I had mentioned that some of this energy from these exergonic reactions is going to be lost as heat. This is what's known as entropy. But the energy that is useful, that can be input into this large amount of energy that's going to be needed for endergonic reactions, is going to be transferred through a special molecule called ATP. And so ATP is in between these two systems. So you have exergonic releasing energy. That energy needs to get donated into these endergonic reactions, and it's ATP that's going to switch back and forth between the two. And so here is ATP's cycle. You can think of ATP as a rechargeable battery that's going to go between the outlets in your house and whatever needs to be charged. Let's say it's your phone, or a remote control would be a better example. So the electricity is being provided by these reactions over here. You store that electricity in the form of a battery. And so when ATP or ADP is the low battery form, and when you need to charge it up, you're going to charge it up by adding a phosphate group. This is a process known as phosphorylation. So the electricity is going to be input or stored into the battery. And the way that it's stored is adding that third phosphate group to ADP. So we go from 2 phosphate groups to 3 phosphate groups by adding this one, and there's energy in that stored bond. When this process happens, it is known as substrate level phosphorylation. Okay, so what that means is the process of adding this phosphate group onto ADP. This arrow is trying to show you that this is an endergonic reaction, and that the energy, which is this little squiggle right here, for adding that phosphate group to ADP is going to come from an exergonic reaction. Typically, it's going to come from cell respiration. So because we are phosphorylating ADP here, we call this phosphorylation. And the energy allowing this process to happen is called substrate level phosphorylation, because we're going to break a substrate into a product and harness some of that energy. Now ATP can be thought of as a charged battery, and what we're going to do is we're actually going to cycle through and break this ATP. We're going to remove that third phosphate group, because that's going to provide the energy when we break it. That's going to provide the energy for these endergonic reactions. And so this right here represents energy that is being released from the breakdown or hydrolysis of ATP being input into this endergonic reaction. So the energy released from exergonic reactions is not directly going to endergonic reactions. Instead, there is a middle cycle here with ATP being hydrolyzed into ADP to provide that energy for these endergonic reactions, and then the ADP and inorganic phosphate then being joined back again by the energy released as this substrate is broken down into this product into recharging that ATP. So in this video, we identified the 2 types of reactions as endergonic versus exergonic. In each type of reaction, we talked about how the change in free energy occurs. In other words, whether delta G was positive or negative. We explained the role of ATP in transferring the energy from exergonic reactions to endergonic reactions. And we also looked at some examples of endergonic, exergonic reactions in terms of whether or not their delta G is positive or negative, what kind of enzymes are going to be involved, catabolic versus anabolic, and some examples of endergonic and exergonic reactions. Exergonic reactions being hydrolysis and cell respiration, whereas endergonic reactions are dehydration synthesis or photosynthesis. I hope this video was helpful. Thanks for watching. Bye.